Hello everyone, and welcome to today's presentation. I'm excited to be here with you to discuss a very important topic, biological oxygen demand, or BOD. On this first slide, you'll see the title Biological Oxygen Demand along with the abbreviation BOD. Over the next few slides, we'll explore what BOD is, why it matters, and how it impacts water quality. We'll also look at how BOD is measured and its significance in environmental management. So, let's get started and dive into understanding this crucial aspect of water analysis. Let's walk through the main sections of our presentation. First, we have the introduction, where we set the stage and outline what we'll be discussing today. This helps establish the context and importance of the topic. Next is the requirement, which covers what is needed or expected to address the problem at hand. Understanding these requirements is crucial for developing an effective solution. Moving on, we have solution preparation, where we plan and design the approach to meet the identified needs. This step is about laying a solid foundation before diving into execution. Then, we look at the process, which details the step-by-step methodology we follow to implement the solution efficiently and effectively. The formula section introduces the key calculations or principles that underpin our approach, ensuring clarity and accuracy. Finally, we arrive at the RESULTS, where we present the outcomes of our efforts, demonstrating how the solution addresses the original requirements and what benefits it yields. Throughout this presentation, each section connects back to our overall goal of providing a comprehensive understanding of the process from start to finish. Let's start by understanding what BOD, or biochemical oxygen demand, really is. It measures the relation between the initial oxygen content on the first day and the remaining oxygen after 5 days of microbial activity. Essentially, it tells us how much oxygen microorganisms consume to break down organic matter in water. This process is called biodegradation of organic matter, and it involves microorganisms breaking down organic compounds. When organic matter interacts with oxygen and these microorganisms, the end products are carbon dioxide, water, and new microbial cells that have grown and reproduced. Similarly, when ammonia is present, microorganisms use oxygen to convert it into nitrate, along with water and new microbial cells. This entire chain of reactions highlights how microorganisms play a crucial role in cleaning and recycling organic pollutants in water systems. Understanding these processes helps us gauge the water's health and its capacity to support microbial life, which ties directly into our broader theme of water quality management and treatment. Now, let's take a closer look at the chemicals we need for this process. First, it's essential to measure our reagents accurately to ensure reliable results. Among the key chemicals, we have manganese sulfate, which plays a role in biological oxygen demand testing. Alkali iodide azide is another crucial reagent, often used in analytical procedures. Sulfuric acid is necessary for pH adjustments and reactions, while starch acts as an indicator in titrations. Salicylic acid and sodium thiosulfate are also important, especially in redox reactions. Sodium hydroxide helps with alkalinity, and potassium biiodate is used in titration processes. When it comes to preparing dilution water, specific chemicals are required to ensure the water's quality. Phosphate buffer solution helps maintain a stable pH, while magnesium sulfate, calcium chloride, ferric chloride, and sodium sulfite solutions are used for various analytical and preparative steps. Moving on to equipment, you'll need incubation bottles of about 300 milliliters in volume. These are standard for biological testing. The BOD incubator provides a controlled environment for proper incubation. And of course, a titration unit is vital for accurate titrations, which are fundamental to many of these chemical analyses. All these chemicals and equipment together form the foundation for precise and reliable testing in our overall process. Now, let's go over the steps for preparing our solution. First, we need to measure out our reagents carefully to ensure accuracy. Starting with manganese sulfate, we prepare a 2M solution. Next, for the alkali sodium azide, we'll take 500 grams of sodium hydroxide and 135 grams of sodium iodide, dissolving each in 1,000 milliliters of distilled water. Additionally, we'll take 10 grams of sodium azide and dissolve it in 40 milliliters of distilled water, mixing thoroughly at room temperature. Moving on, we need concentrated sulfuric acid, which will be used in subsequent steps. For the starch and salicylic acid, we'll dissolve 2 grams of starch and 0.2 grams of salicylic acid in 100 milliliters of hot distilled water. Then, for the sodium thiosulfate solution, we weigh out 6.205 grams of sodium thiosulfate and 0.4 grams of sodium hydroxide pellets, dissolving both in 1,000 milliliters of distilled water. Next, for potassium hydrogen iodate, we carefully weigh 812.4 milligrams, which is 0.8124 grams, and dissolve it in a small amount of distilled water within a 1,000 milliliter volumetric flask. Now, let's discuss the phosphate buffer solution. We dissolve 8.5 grams of KH2PO4, 21.75 grams of K2HPO4, 33.4 grams of NUT-HPO47H2O, and 1.7 grams of NH4Cl in about 500 milliliters of distilled water, then dilute to a full liter. The key point here is ensuring the pH reaches exactly 7.2, which is critical for our buffer's effectiveness. For magnesium sulfate heptahydrate, we weigh 22.5 grams, dissolve it in distilled water, and then dilute to 1 liter using a volumetric flask. Similarly, for calcium chloride, we dissolve 27.5 grams in distilled water and make up to 1 liter. Finally, for the ferric chloride solution, we dissolve 0.25 grams of FeCl36H2O in distilled water and dilute to 1 liter. Throughout this process, the most important concepts are precise weighing, thorough mixing, and maintaining the correct solution concentrations. These prepared reagents will serve as the foundation for our experiments, ensuring accuracy and reproducibility in our results. Let's walk through the process step by step. First, we prepare our dilution water by adding 2 milliliters per liter of specific reagents into distilled water. These reagents include phosphate buffer, magnesium sulfate, calcium chloride, ferric chloride, and sodium sulfite solutions. The purpose here is to create a consistent environment for our measurements. Next, for each sample, we take 300 milliliters and place it into a BOD bottle. Of course, you can adjust the volume if your procedure requires. We then prepare 2 sets of this sample, one for immediate dissolved oxygen measurement and another to incubate for 5 days. To each set, we add 1 milliliter of alkali azide, followed by 1 milliliter of manganese sulfate solution. After adding these reagents, we shake the bottle thoroughly to mix everything well, and then let it sit so the precipitate can settle. After that, we add 2 milliliters of concentrated sulfuric acid, carefully cap the bottle, and shake it again until all the precipitate dissolves. This step is crucial because it prepares the sample for accurate dew analysis. One set will be analyzed right away on day 1. This is our initial sample. The other set goes into a BOD incubator at 20 degrees C for 5 days, where it will undergo biological oxygen demand testing. This process ensures we accurately measure the oxygen consumption over time, which is central to understanding water quality. Remember, precise preparation and timing are key to reliable results. All right, let's walk through the process. First, we take about 100 milliliters of our sample and transfer it into a conical flask. Then, we start titrating it with a standard sodium thiosulfate solution, which has a normality of. We add the titrant slowly until the solution's color shifts from dark yellow to a light yellow, indicating that we've reached the endpoint of the titration. Next, we add a few drops of starch indicator. This helps us see the exact point where the iodine is fully reduced. We continue titrating until the solution becomes either colorless or returns to the original sample color. It's important to note the volume of sodium thiosulfate used during this titration, as it will be crucial for calculating the dissolved oxygen in our sample. Moving on, we measure the initial dissolved oxygen, or dew, in our samples at time 0. After that, we incubate the samples at 20 degrees Celsius for 5 days. This incubation simulates natural conditions and allows the bacteria to consume the organic matter, reducing oxygen levels over time. Finally, after 5 days, we come back to the lab and record the remaining dissolved oxygen. Using these measurements, we can calculate the BOD, or biological oxygen demand, which tells us how much oxygen was consumed during the incubation period. This process is vital in assessing the organic pollution load in our samples and understanding the health of the water body. All right, let's walk through the calculation process for BOD measurement. First, we have the formula for DO, or dissolved oxygen, which is expressed as DO in milligrams per liter. The formula is DO equals the volume of titrant in milliliters multiplied by the normality of sodium thiosulfate, times 8, times 1000, all divided by the product of V2 times the quantity V1 minus V, and then divided again by V1. Now, V is the volume of reagent used, and in this case, it's equal to 1 plus 1, which gives us 2 milliliters. V1 is the total volume of the sample, which is 300 milliliters, and V2 is the volume of the titration sample, set at 100 milliliters. These values are key because they help us standardize the calculation for the DO. Next, the BOD, or biochemical oxygen demand, in milligrams per liter, is calculated as the difference between DO readings at 2 different points, DO1 and DO5, divided by the dilution factor, DF. The dilution factor itself is calculated as 300 divided by S, where S is the aliquot sample volume taken for analysis. By understanding these formulas and how each component interacts, we can accurately determine the organic pollution level in water samples. This process ties into our overall theme of assessing water quality, ensuring we have reliable data to make informed decisions about environmental health. Let's take a closer look at the data from our samples. On day 1, we took a 300 ml sample and measured a titrant volume of 4.9 ml, with a numerator reading of 980. The denominator remained constant at 99.33, which is important for our calculations. The dissolved oxygen, or DO, was 9.87 mg/L on day 1. By day 5, the titrant volume decreased to 4.1 ml, and the numerator reading dropped to 820. The denominator stayed the same at 99.33, indicating consistency in our measurement process. The DO level on day 5 was 8.26 mg/L. Now, to understand the biological oxygen demand, or BOD, we look at the difference in DO between day 1 and day 5, which is 1.61 mg/L. Furthermore, we performed a smaller sample test by taking 5 ml of water, adding 295 ml of distilled water, resulting in a total sample volume of 5 ml plus 295 ml, and a dilution factor of 60. The BOD calculated from this diluted sample was approximately 0.0268 mg/L. This process allows us to determine the BOD levels accurately, which are vital for assessing water quality. The key takeaway here is how the titrant volumes and DO levels change over time, giving us insight into the organic pollution levels in the sample. Let's take a closer look at BOD levels and what they tell us about water quality. When BOD is between 1 and 2 milligrams per liter, it indicates the water is very clean, with very minimal organic pollution, making it safe for aquatic life and human use. Moving to the 2 to 5 milligrams per liter range, the water is moderately polluted and may contain some domestic sewage, but it's not yet critically harmful. As BOD levels rise to between 5 and 10 milligrams per liter, the water quality drops significantly. This range is considered poor, with a high organic load that can be harmful to aquatic organisms and disrupt ecosystems. And when BOD exceeds 10 milligrams per liter, we're looking at heavily polluted water, which becomes dangerous for aquatic life and indicates serious environmental concerns. To put this into perspective, untreated sewage often has BOD levels between 200 and 600 milligrams per liter, which is extremely high. This comparison highlights how much pollution can be present if sewage isn't properly treated, emphasizing the importance of wastewater management to protect our water resources. Understanding these BOD levels helps us gauge water health and the urgency of pollution control, all of which ties back to our overall goal of safeguarding water quality for ecosystems and human communities alike.